This is section 7.3, part A, the sampling distribution of X bar. Mean and standard deviation of a sampling distribution of X bar. Suppose that X bar is the mean of a simple random sample of size n drawn from a large population that has a mean of mu and a standard deviation of sigma. Then the mean of the sampling distribution of X bar, or the average of all your X bars together from the different samples, will just be equal to the mean of your entire population. And the standard deviation for your samples will just equal the standard deviation of your population divided by the square root of the number of samples, as long as that 10% condition is met. And remember, the 10% condition says the sample size must be less than or equal to 1/10 of the entire population. The behavior of X bar in repeated samples is much like that of the sample proportion p hat that we talked about in the previous section. The sample mean X bar is an unbiased estimator of the population mean mu. The values of X bar are less spread out for larger samples. Their standard deviation decreases as the rate of the square root of the sample size. So you must take a sample 4 times as large to cut the standard deviation of X bar in half. So because the sample size, you're taking the square root of it. If you want to cut it in half, 2 squared is 4, so you would have to take a sample size that is 4 times as large. You should use the formula of theta over the square root of n for the standard deviation of X bar only when that 10% condition has been met. Notice that these facts about standard deviation and mean are true no matter what the shape of the population distribution has. So even if the original population is extremely skewed to the left or skewed to the right, you're still going to use these same rules to find mean and standard deviation of your sample proportions or your sample distribution. Sulfur compounds such as dimethyl sulfide are sometimes present in wine. DMS causes off odors in the wine, so winemakers want to know the odor threshold. The lowest concentration of DMS that a human nose can detect. Extensive studies have found that DMS odor thresholds for an adult follow roughly a normal distribution with a mean of 25 micrograms per liter and a standard deviation of 7 micrograms per liter. Suppose that we take a simple random sample of 10 adults and determine the mean odor threshold of X bar for the individuals in the sample. What is the mean of the sampling distribution of X bar? And we need to explain. Since we know that X bar is an unbiased estimator of mu, then the mean of all of our X bars will just equal the mean of the entire population, which is 25 micrograms per liter. What is the standard deviation of the sample distribution of X bar? Check the 10% condition is met. So first, let's check the 10% condition. Our sample size is 10. So 10 times 10 tells us that our population would at least have to be 100 adults. We know there is definitely more than 100 adults in the population, so our 10% condition is met. To find your standard deviation, you are going to use the formula of the standard deviation for the population divided by the square root of the sample size. Or in this case, 7 divided by the square root of 10, which will give us 2.214. We have described the mean and the standard deviation of the sampling distribution of a sample mean, but not its shape. That's because the shape of the distribution X bar depends on the shape of the population distribution. In one important case, there is a simple relationship between the two distributions. So in this activity, we would need access to a computer, and we would do an applet investigation that's going to look at the sample sizes for different original populations. So this is what it would look like to begin with. If this is the population to start with, you would take samples of size 5, and then you would calculate the mean of that sample. So this is if we do 5 different samples, and this is if we do 10 different samples. So there our choices from the population distribution. We can start with a normal, uniform, skewed, or custom. And then during this activity, we would look at a normal distribution, a skewed distribution, and see what would happen. From this activity, you will see that if the sample size is large enough, that even if it is skewed to begin with, the sample distribution will end up being normal. So if the population distribution is normal, then so is the sample distribution. So if the original is normal, the sample distribution will also be normal. This is true no matter what the sample size. So it doesn't matter if you do a sample size of 5 or do a sample size of 500. If the original population is normal, the sample distribution will also be normal. Sampling distributions of sample mean from a normal population. So suppose that our population is normally distributed with a mean of mu and a standard deviation of sigma. Then the sampling distribution x bar will also have a normal distribution with a mean of mu, and its standard deviation will be sigma is equal to the sigma divided by the square root of n, provided that we've already checked that the 10% condition has been met. We already know that the mean and standard deviation of the sampling distribution. All we have to add is the normal shape. Now we have enough information to calculate probability involving x bar when the population distribution is normal. So the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. Show your work. So we already know that the population is normally distributed. Since the population is normally distributed, we know that the sample will also be normally distributed. We're going to let x be the height of a randomly selected young woman, and we need to find the probability that x is greater than 66.4. Since we know these are normally distributed, we can find our z value. And we know the formula for z is x minus mu over sigma. So we're going to do 66.5 minus our mean of 64.5 and then divide it by our standard deviation of 2.5, and that will give us a z value of 80 or 80%. We want to find the probability that anyone would be taller than this. So we need to find the probability that the z-score is greater than 0.08. Remember on your table, this tells you the probability that is less than a specific value. So the probability that z is less than 80 would be 0.7881. But since we're looking for the probability that is greater than, we would do 1 minus the probability that it is less than, and this will give us 0.2119. So the probability of choosing a young woman at random whose height exceeds or is greater than 66.5 inches is about 21%. Find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches. Now in that previous example, we were just talking about one young woman, so we used the population mean and standard deviation. Because we are talking about a simple random sample, now we're going to have to find the new mean and the standard deviation for the sample itself. So we are going to check that the 10% condition is met before we can do anything else. And if we do 10 times our sample size of 10, that would give us 100 young women. We can about guarantee in the entire population for the United States, there will be more than 100 young women in our population. So we can go ahead and do our calculations. Remember, the mean of all of your sample means, or the mean of your x bars, is just equal to the mean for the entire population. So our mean, or our mu x bar, is still going to be 64.5 inches. We do have to find the new standard deviation, and our sigma sub x bar is equal to our standard deviation for the entire population divided by the square root of n, or 2.5 divided by the square root of 10, which is going to give us 0.79. Since the population distribution is normal, the value for x bar would also be normal, and it would have a normal distribution with a mean of 64.5 inches and a standard deviation of 0.79 inches. Now that we have this information, we can go ahead and find our probability. So we're finding the probability that x bar, not mu, is greater than 66.5 because now we're talking about a sample. We're still going to start by finding that z-score. Remember, z is still x minus mu over sigma. So we're still going to do 66.5 minus 64.5 all over our new standard deviation of just the sample, which would be 0.79. And this is going to give us a z-value of 2.53. Again, you would go to table A to look up your z-value to find the probability or the area. And the area to the left of 2.53 would be 0.9943. But we're looking for greater than, or the area to the right. So the whole area is 100%, or 1. So 1 minus the area to the left will tell us the area to the right, which is 0.0057. So it is very unlikely, actually less than 1% chance, that we would choose a simple random sample of 10 young women who average have a height that exceeds 66.5 inches. Let's check our understanding. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with a mean of 266 days and a standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days and show your work. Now this is just for one specific female, it's not for a sample, so we will use the population mean and standard deviation. We are looking for probability, so we are going to start by finding that z-score. And remember, z is equal to x minus mu over sigma. If we do this, we're going to find our z-value is 0.25. So we want to find the probability that z is greater than 0.25. Remember, on the table, or table A, it tells us the area to the left. So if 0.25 was right here, the area on the table shows me what's to the left. But we want to know greater than that value. So if we do 1 minus the area on the table, that'll tell us the probability. So there's about a 40% chance that a female can have a pregnancy that lasts more than 270 days. Suppose we choose a simple random sample of 6 pregnant women. Let x bar equal the mean pregnancy length for the sample. What is the mean of the sampling distribution of x bar? And explain the meaning. Since the mean of the sampling distribution of x bar is the same as the mean for the distribution of x, we know that mu sub x bar will just be the same as our mu sub x, so it would still be 266 days for the sample. Now, we need to compute the standard deviation, but we do need to check that 10% condition. So if we're talking about all pregnant women, 6 times 10 would give us 60, so our population would at least need to be 60 females. We can about guarantee that there's more than 60 pregnant women, so that 10% condition is definitely met. Because we are talking about a sample size of 6, we will need to find the new standard deviation. And remember, the formula for that is the standard deviation for the population divided by the square root of n. Or, our standard deviation was 16 days, we're going to divide that by the square root of 6, and that will give us the standard deviation for the sample to be 6.532 days. Suppose that we chose a simple random sample of 8 pregnant women. Let x bar be the mean. Find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Now, since we are talking about the entire sample, we will now use our new mean and our new standard deviation for just the sample. So the mean and standard deviation in this case, the mean is still 266, but our new standard deviation was at 6.532. To find this, you are going to find the z value again. Anytime you're finding probability, you're going to use the z. Remember, z is equal to x minus mu over sigma. And if we do our x minus mu over sigma, we will get a z value of 0.61. Now again, exceed means greater than. So if you want to find the area greater than, you will have to do 1 minus the area on the table. So if you look up a z value of 0.61, it's going to give you an area of 0.7291. So 1 minus the area to the left will tell us the area to the right, or our probability that it exceeds. So there's about a 27% chance that of our sample of 5 women, the average of all 5 women will exceed 270 days for the length of their pregnancy.